Welcome back to McNab Chemistry. Today we're going to have a look at an extension question around the formation of enantiomers during chemical reactions. So when chiral compounds form in chemical reactions, we don't always get both enantiomers produced, so we don't always form racemic mixtures. So let's try and understand why that might be the case. Right, so if we have a look at this, so hopefully then from previous videos we're able to recognise what makes an organic molecule optically active, i.e. the presence of a chiral carbon. That means that we've got a carbon with 4 different groups around it which can be arranged differently in space. In the D enantiomer and the L enantiomer, the atoms are arranged in the space around the chiral carbon differently, making them rotate plane polarized light in the opposite directions. So that's a summary of what we already know. So let's have a look at the definition of stereoisomerism now as well. So remember the definition for stereoisomerism: molecules which have the same structural formulae but the atoms are arranged differently in space. However, what if in a reaction mechanism the reactants can only enter each other's space in one way? So this is the big question, and this is the extension question. So let's have a look at that question again. So what would happen if in a chemical reaction mechanism the reactants can only enter each other's space in one way? So when they actually collide in the reaction, they can only collide by bumping into each other via one route. So the answer is only one of the enantiomers will form when products are produced. So if the reactants can only enter each other's space in one particular way, then you only get one enantiomer. Right, so at A level we need to know that when the nucleophile Cn- attacks a delta positive carbon in ethanal, it can attack the space around the delta positive carbon with equal probability from both sides. And this results in a 50% mixture of both enantiomers, thereby forming a racemic mixture. Right, so this is what you do have to know at A level. And it's a very standard exam question, it comes up a lot. So here I've got functional group CHO, so that's meth, eth, that's ethanal. And we can see here that the Cn- can attack that delta positive carbon from that side, and the Cn- could attack the delta positive carbon from that side. And they can do that with equal probability. So because they can attack from that side and from that side, we get these two products. The Cn joins onto the carbon on the left hand side there, and the Cn joins onto the carbon on the right hand side there. So we get the D and the L forms of the enantiomer. So we would end up with a racemic mixture. So that will be that's a nucleophile, and it's being added to the molecule, so that would be nucleophilic addition. So in nucleophilic addition reactions we do get racemic mixtures produced. So here's the extension question. However, if in a reaction mechanism the reactants cannot approach each other from both sides and react, both enantiomers of the product, even though the product has a chiral carbon, will not be formed. So you can have a molecule that's got a chiral carbon, which does rotate plane polarized light. That's completely different from thinking about a chemical reaction that produces only one of the enantiomers from that chemical reaction. So an example of this is in the nucleophilic substitution reactions. So if we're forming butan-2-ol from 2-bromobutane, we also have to assume that the starting molecule of the 2-bromobutane was a single enantiomer. That's also really important. I have to have as my starting reactant 2-bromobutane, which is just one of the enantiomers of 2-bromobutane. Okay, right, so the hydroxide ion always attacks from behind, always producing the same enantiomer. So if I start off with this single enantiomer of 2-bromobutane, okay, the OH minus can only attack that carbon from one side. Okay, so therefore I always get this product, which is just one enantiomer of butan-2-ol. Okay, so the key here is this is nucleophilic substitution. So the formation of single enantiomers in nucleophilic substitution is possible if our starting reactant is a single enantiomer. Okay. Right, so in conclusion, if the chiral molecule is produced by a substitution reaction and the starting molecule is a single enantiomer, then the attacking species can only attack from one side and a single enantiomer will be produced. So therefore, nucleophilic substitution reactions produce single enantiomers provided that the substrate was also a single enantiomer, whereas nucleophilic and electrophilic addition reactions always produce racemates, so always produce mixtures containing both enantiomers. Okay, just one more time to make sure you understand that. Okay, so nucleophilic substitution reactions produce single enantiomers provided that the substrate, i.e. the reactant that we started with, was also a single enantiomer. Okay, however, nucleophilic and electrophilic addition reactions always produce racemates. So therefore, nucleophilic and electrophilic addition reactions always produce mixtures containing both enantiomers. Okay, thank you for watching. I hope that's been helpful. Don't forget to like and subscribe and click on the bell notification to stay fully updated.